All right, good morning again, everyone. Welcome back from the break. Our last talk of the morning is from David Hall at NVIDIA, and he'll be discussing deep learning architectures.
Okay, hi.
Oh,
Yep.
David, can you switch your presenting mode? Or click the swap displays.
Yep.
All right, cool.
That work?
Yep.
Okay. Hi, I'm David Hall, and I'm pleased to speak with you all today at the AI for Earth System Science Summer School. In this talk, I will attempt to summarize the field of deep learning and some of its many and varied architectures for you. I'm planning to cover a lot of material in this talk. In the end, I just want the important ideas to be familiar to you, so you can look things up when you need them. If deep learning is new to you, remember you can always come back to review the slides, the recording, or you can contact me directly with questions. So deep learning is a type of machine learning where large models, often with millions or billions of parameters, are trained to make predictions. The main idea behind deep learning is simple: build functions by automatically reverse engineering them from examples. Despite this, there remains a great deal to know about this subject. There is an entire zoo of deep learning models in the literature, each of which is specialized for a different task. These models may be thought of as design patterns in a new form of code development. Some of the most important models and techniques one should be familiar with are listed here. This list is far from exhaustive. To use deep learning well, it's best to know which model to use, why it works, and when we should customize it or build our own. The central idea behind deep learning is that given many examples of how our function should behave, we can reverse engineer that function without requiring an expert to carefully define specific features. In this way, deep learning differs from traditional machine learning techniques. Instead of writing software explicitly, we define it implicitly by examples of what we would like it to do. Functions constructed in this way automatically learn the features needed to make predictions, even learning complex hierarchies of features. The idea of learning any function from data automatically is clearly an idealization. If we could produce any function this way, we would have a universal problem solver, and no skill would be required on our part to build the software, just great data. This is an aspirational goal, but it's a long way off. In the meantime, we need to have some skill and intuition to construct effective machine learning solutions. Since most of the members of this audience are new to AI, I think it makes sense to review some basics of deep learning rather than focusing on the latest state-of-the-art techniques. However, if you'd like to keep up with the latest developments in AI, you should look at Archive Sanity and Papers with Code. Archive Sanity helps distill which papers are most important and influential over different time periods. And Papers with Code keeps track of which models exhibit the highest skill on a given task. These are my go-to resources for keeping up with AI. Twitter and YouTube are tied for third, and the Distill website is pretty good too. So here's a list of the subjects I plan to cover with models in each, starting with the basics of deep neural nets, and then introducing some of the main design patterns found in deep learning. Before we visit each of the models living in the deep learning zoo, I'm going to review some of the basics of what deep learning is and how we can use it. If we don't understand these concepts, there's little point in learning the finer details of the model zoo. Karthik did an amazing job, in my opinion, introducing deep learning basics, but I don't think it hurts to hear a few things twice. So machine learning works by reverse engineering functions from a large set of examples of how it should behave. Given many input and output pairs, we use an optimizer to search for a function that fits that data well, but also generalizes to new values. To ensure that it is generalizing well, we have to hold back some of our training examples to see how well they can be predicted. In my opinion, the best way to think about machine learning is that it's an alternative way to build software. Software is composed of a set of functions that take one set of values as input and return a different set of values as output. As an example, we might wish to build a function to predict how much precipitation is expected within a region, given its mean temperature, pressure, and water vapor. On the left hand is a handwritten function composed of mathematical operations with a set of subroutines, and on the right is a machine learning function composed of mathematical operations with a set of adjustable parameters. The idea is that once we have properly adjusted those parameters, the function on the right can do just as good of a job of predicting the correct output as can the handwritten version. And for challenging applications, it can often do far better. Machine learning is particularly well suited to operations that deal with complex real-world phenomena, which are not easily quantified. For example, while some of the people here might be able to identify an atmospheric river by eye in this image, most of us would probably find it pretty challenging to build a heuristic algorithm that is able to do so automatically. In cases such as these, it's simpler to label a large set of examples as containing an atmospheric river, or not, and allow an optimizer to automatically search for the appropriate characteristics that distinguish the two classes. The machine learning approach to software development is complementary to traditional software development. Each set of tools has its strength, and the two are most effective when used together. However, since much of machine learning has only recently become practical, rapid progress is possible by making use of these new techniques. While machine learning can be very powerful, I don't want you to think it's mysterious. So let's cut to the chase here. Machine learning is just a generalization of curve fitting. Or alternatively, traditional curve fitting may be seen as the low dimensional limit of machine learning. It's important to understand this, as much of the intuition needed for machine learning and deep learning comes from traditional curve fitting and optimization. However, many things change in very high dimensional spaces. AI is the art of making computers do clever things. The definition of artificial intelligence has been evolving since computers were invented. Most early approaches took the form of expert systems or direct symbol manipulation. Machine learning is a type of AI which tries to build functions from data rather than decode them by hand. Deep learning, also known as artificial neural networks, is a type of machine learning that deals with large models. Deep learning differs from other machine learning techniques in that it tries to learn everything it can from the data, eliminating the need for an expert to handcraft problem-specific features. Although if artificial neural networks were inspired by neurons in the brain, real neurons are much more sophisticated. Artificial neural nets are just a set of simple equations with a set of adjustable parameters. Despite this, the power and the effectiveness of this technique should not be underestimated. Often these equations are represented as simple networks of activation functions and weights, reminiscent of biological networks. When you're performing curve fitting, a good model is one that generalizes well to new unseen data points. We need to avoid overfitting. We can control this by adjusting our model capacity or by one of many regularization techniques. The ultimate size and accuracy of your model is limited by the data you have available. If you only have 10,000 independent examples, then your model should have no more than 10,000 adjustable parameters. A good rule of thumb used by some people is to have about 30 data points for each adjustable parameter. We measure model generalization by applying it to input it's never seen before. To do so, we need to set aside some of our data for testing the final result. If we want to tune hyperparameters, we also need to set aside a validation set. It's important not to use your test data for training, or you'll have no idea if your model actually generalizes. In supervised training of machine learning models, the major components involved are the data, the model, the loss function, and the optimizer. The training data implicitly describes the behavior we wish our model to learn. The model is the equation we've chosen to fit the data. The loss function measures the error in our fit, how well we're doing. The optimizer is a search strategy, which iteratively adjusts the parameters of our model to try and find a low loss. There are many choices to be made for each of these components. Parameters associated with these choices are called hyperparameters. Training our model means searching for a good solution. It is the optimizer's job to try out different adjustable parameters until it finds a set that produces accurate predictions. There are many search strategies our optimizer could use. You could use grid search, evolutionary algorithms, conjugate gradient, or other things. But what is actually used in practice is some variation of the simplest approach, gradient descent. For large models, the other techniques tend to be more expensive and less reliable. When we train our model, we're starting our weights off with random weights and applying some variant of gradient descent. We iteratively follow the loss function downhill until we find a minimum, which has a much smaller error than the function we started with. Each time we train, we start from a different random point and we can get a different answer. Our random initial points start in some limited range. Normalizing or rescaling our data ensures that our initial points cover the surface reasonably well. In order to perform gradient descent, we need to compute the gradient of the loss function with respect to the model parameters. This gradient is computed by the algorithm called backpropagation. The error is evaluated at the output, and then blame is distributed appropriately to each of the weights in the model. This is just an efficient recursive application of the chain rule. Each weight can then be nudged upward or downward by a little bit to produce a result with slightly less error. In order to perform backpropagation, we need to be able to compute the gradient of an arbitrarily complex function. Writing the gradient for our model by hand is tedious and error-prone, and it used to be a barrier for model development. Luckily, modern deep learning frameworks make it easy for us by building the gradient function automatically. In order to build your own machine learning application, you're going to need a large set of labeled data, a machine learning framework to simplify the coding, and a large amount of compute to train it, preferably in the form of a GPU accelerator. There are a lot of deep learning frameworks to choose from, but presently the most popular and well-supported choices are written in Python. Personally, PyTorch would be my #1 choice, although TensorFlow with Keras is also a very popular choice. Another very strong contender worth considering is the Julia language with its Flux machine learning framework. Julia has many advantages to recommend it, including readability, excellent performance, a large set of packages, and the ability to easily interface with other languages such as Python, C, and Fortran. GPUs are the tools that make machine learning practical. With a GPU, you can train a machine learning model in minutes or hours. Without it, the same model will take you days or maybe even weeks. And the compute advantage provided by GPUs grows larger every year. While year-over-year performance growth of CPUs has slowed to a trickle, the opposite is true for GPUs, with the latest generation of NVIDIA's A100s providing 20 times the peak performance of the previous version. So conversely, machine learning makes GPUs more accessible. Not only can you build next-level functionality using machine learning, but these functions are automatically optimized for GPU acceleration. In the end, you have powerful GPU-accelerated software without having to port the code and without having to maintain multiple versions. There's lots of ways to gain access to GPUs. Of course, you can always purchase your own GPU-powered laptop, desktop, or workstation, but you can also use GPUs in the cloud, and most cloud computing providers offer free credits to help you get started. You can access your institutional supercomputers or submit an application for compute time on one of them. Finally, Google's Colab service provides a Jupyter Notebook type environment with access to a single NVIDIA GPU for free. All right, so now that we've reviewed the basic concepts, let's visit the first and simplest network in our zoo, the fully connected network. A fully connected network is one in which a given neuron is connected to every neuron in the previous level. As there are so many connections, their memory and compute requirements tend to be pretty large. Fully connected networks have an arbitrary number of layers, and each layer can have a different number of neurons. For historical reasons, if the model has a single layer, it's called a shallow network. If it has more than one layer, it's called a deep network. Fully connected networks are better suited to smaller problems due to their large model size. However, for small problems of this size, other techniques like random forests are also very competitive. A shallow single-layer neural network can be viewed as a series expansion over a set of basis functions, similar to a Taylor series or a Fourier series expansion. Ideally, the basis functions in our series should match the function we're trying to represent. For example, if our function is periodic, we would want a Fourier basis. Otherwise, we might use a Taylor series. Using the same simple basis functions for each neuron, such as a rectified linear unit, we're able to construct piecewise linear approximations of pretty much any function. By training a neural network with 2 layers, the model can learn the target function and the best basis functions to use at the same time. In this picture, we see that our model is still just the sum of 4 basis functions, just like the last slide. But in this case, each of the bases, phi1 through phi4, is itself a function that has been learned from the data. In this way, our basis functions are automatically customized for the data they need to represent. Deep neural networks with multiple layers are able to learn a hierarchy of features from the data. A good example is finding features of a face. The input is a set of pixels, and the output is the probability of detecting a face. In order to produce the right answer, the model learns a hierarchy of edges, curves, parts, and objects. The deeper the network is, the more levels of abstraction it's able to identify. This is how Jeffrey Hinton and his student, Alex Krzyzewski, were able to beat the world's best experts at the ImageNet challenge. They trained a deep neural network that was able to automatically learn its features from the data. They didn't have to hand code custom feature extractors for each object type, and training the model required no expert knowledge of the dataset. Their model learned the features and learned to classify them at the same time. GPU acceleration was also critical to their success. It took 5 to 6 days to train their model on 2 NVIDIA GPUs at the time. Without it, it would have taken weeks and been impractical to repeatedly train and test the network. Their network, named ALEXNET, was actually a convolutional neural network rather than a fully connected network, which is what we'll cover in the next section. Possibly the most well-known type of deep learning model is a convolutional neural network. For low-dimensional data, random forests are competitive with neural nets. However, neural nets come into their own when dealing with images, sounds, and other high-dimensional data. CNNs detect translationally invariant features in data. In other words, if you train a network to detect an object in one part of the image, it should be able to detect that same object anywhere else in the image. While CNNs are most often applied to computer vision tasks, they're also effective for identifying time-invariant features like sounds and 3D spatial invariant features found in computational physics simulations. Within the area of computer vision, there are different tasks we might wish to automate, and each task tends to use a different set of specialized networks. Classification is the identification of a single object type in an image. Localization identifies the object and its position. Detection involves identification of multiple objects and their locations within an image. And segmentation is the classification of each pixel separately. Instance segmentation performs both detection and segmentation on each object. Since classification is the simplest, we'll focus on that first. Given an image, the goal is to identify the dominant object or feature present in that image. Our target classes could be handwritten digits, cloud types, severe weather events, galaxies, or any other object of interest. In this example shown here, the goal is to convert visible images from satellites into one of many possible land use classifications, such as beach, forest, river, runway, or residential. When classifying images, the input is a set of pixels, and the output of your function is a set of numbers, one for each possible class. For example, for the MNIST dataset, there are 10 handwritten digits to identify, composed of the numbers 0 through 9. Each output is a learned function representing how likely it is that the input matches its digit. Then the maximum of those is taken as the prediction. It might seem like quite a conceptual leap to jump from 1D curve fitting to building networks that take images as input, but it becomes easier to understand when we think of images as points or vectors with multiple dimensions. For example, a point in 3D space can be represented by 3 numbers, x, y, z coordinates, for example. These coordinates can be lined up in a row to form a vector. An image, when flattened out into a string of values, is also just a vector, but instead of 3 dimensions, it might have a few hundred or a million dimensions. Neural networks are just functions that map points to points, or vectors to vectors. Sometimes the points have many dimensions, sometimes just a few, but the concept remains the same in both cases. Fully connected networks and high-dimensional inputs, unfortunately, don't mix very well. They produce huge networks that require 5 too much data and compute time to train. While conceptually we could train a fully connected network on images, for larger images, this becomes impractical. Each neuron in the first layer is connected to every pixel in the input. So for a 1 megapixel image, this would mean 1 million weights just for a single neuron. And would need a similar number of neurons to account for every possible location of our target within the image. Fully connected networks don't scale well with the input dimension. This is why convolutional neural networks were invented. CNNs explicitly encode the idea of translational equivariance, or invariance. That is, as we move an object from point to point within an image, like this kitten, it should be identifiable as the same object, regardless of its location. In order to learn this implicitly in a fully connected network, we would need to provide examples with the object at many, many locations. CNNs save an enormous amount of training by encoding this idea explicitly in the network. So convolutional neural networks train a set of small matrices called kernels or filters. Each kernel is a feature detector which can be applied to a small region of the input. If the feature is present, the output value is large. The kernel, when applied in parallel to every possible location in the image, produces a transformed image as the output, as discussed very clearly by Karthik. Here is an example of a handcrafted convolution. The small matrix GX detects horizontal edges and GY detects vertical edges. When combined into G, they're able to detect edges at any angle. This filter is called the SOBEL filter. When we apply the SOBEL filter, its output is an image of the same size or similar size where object edges have been identified. A CNN uses small kernels like these, which are learned directly from the data rather than coded up by hand. So now that we've introduced convolutional neural nets, let's see how they have been used to classify images over time. CNNs have been around for 2 decades, but they have become larger, more effective, and far more widely used over time. Here's a brief timeline of their application to image classification, beginning with Yann LeCun's LEARNING, followed by ALEXNET, VGG, and RESNET. In 1998, Yann LeCun and his collaborators constructed one of the first convolutional neural networks that was trained automatically using backpropagation. They built a network with 5 convolutional layers and 60,000 parameters, which they applied to the task of classifying handwritten digits for banks and the US Postal Service, such as those found in the MNIST dataset. Despite the success of LEARNING 5, CNNs did not become immediately popular for computer vision tasks. GPUs were not yet available, and using CPUs to train the network was very slow and very expensive. Other models, like support vector machines, did just as good of a job at classifying these digits while requiring less compute time. In order to facilitate progress in computer vision and AI model development, the ImageNet database was constructed by Fei Li and collaborators, containing millions of images with 20,000 different categories. They also established the ImageNet Large-Scale Visual Recognition Challenge as an annual competition challenging researchers to submit algorithms capable of automatically identifying images from a set of 1,000 different classes. The first competition was held in 2010, and each year the top model accuracy increased rapidly. Jeffrey Hinton and his student Alex Krzyzewski constructed an 8-layer CNN named ALEXNET that won the ImageNet competition in 2012. The model achieved a top 5 error that was more than 10% lower than that of the runner-up. The model had 60 million parameters, about 1,000 times as large as LEARNING 5 was, and was trained for several days on 2 NVIDIA GeForce GPUs using NVIDIA's new general-purpose CUDA software. This model was not the first to use GPUs or CNNs. Nevertheless, it made a huge splash due to its amazing performance in the competition. It demonstrated that a neural network trained on data alone could handily beat the handcrafted solutions of the world's top experts. The ALEXNET paper has been one of the most influential in computer vision and has been cited over 60,000 times. In 2014, the VGG16 network came in 2nd place in the competition. It's a 16-layer model with a total of 138 million parameters, twice as large as ALEXNET, which was trained for 2 weeks on 4 NVIDIA GPUs. What was remarkable about this network is its simplicity and depth. The network demonstrated the advantage of network depth on model accuracy. Pre-trained versions of the VGG16 model are still often used as a feature extractor for other neural networks. The first place winner in 2014 was the GOOGLENET model, also referred to as the inception model. Its top 5 error rate of only 6.6% was comparable to the human error rate on ImageNet. They used a multipath network in-network design called the inception model that combined convolutions of different sizes in parallel in order to approximate a sparse matrix structure. This approach achieved higher accuracy than VGG16 while using only 5 million parameters instead of 138 million. This network in network design has been used subsequently in many models. So many of the classifiers discussed so far apply convolutions in the first few layers to discover feature vectors, which are then sent as lower dimensional inputs to several fully connected layers at the end. In 2015, a team at Berkeley realized you could readily replace the fully connected layers with one-by-one convolutions. They perform an equivalent operation but allow you to process multiple images in parallel. By applying fully connected network to an image larger than its receptive field, you can classify each section of the image in parallel as if the entire classification network was a single large convolution. This pixel-wise classification approach is a precursor to the segmentation networks we will discuss shortly. The next step in deep learning neural net evolution was the RESNET. As of 2015, two distinct trends were becoming really obvious. Each successive classifier to win the ImageNet competition had more layers than the previous model and correspondingly more parameters. The large neural nets trained on larger quantities of data led to more accurate solutions. Unfortunately, networks deeper than about 20 layers showed no further improvement. And in fact, their accuracy started to fall off when you added more layers. RESNETs, which we discussed in this section, overcame this problem. The main reason networks deeper than 20 layers were failing is the problem of vanishing gradients. In order to train a neural network by backpropagation, the error needs to be distributed to each weight using the chain rule. Each time it splits, the signal gets exponentially smaller and more dominated by noise, until after 20 layers, the signal is lost in the noise and training no longer converges. In the image on the right, we see the deeper CNNs actually perform far worse than the 20-layer CNNs when applied to tasks like image classification. Another major and somewhat embarrassing issue was the observation that most neural networks had a hard time learning the identity function, where the output is just a copy of the input. Starting from random weights, deep neural networks required a lot of training before the networks converged on the identity function. As far as such a network is concerned, the identity is just another function to learn, no more or less difficult than any other. However, since that information was available at the input, something seemed to be clearly missing from the standard network design. The solution to both the vanishing gradient and identity problems turns out to be a simple but powerful idea. We can just add the input of a layer or block of layers onto its output, making a so-called skip connection, so long as the output size matches. Then when the chain rule is applied during backpropagation, gradient information can flow along the skip connection without decaying. It also makes it simple to learn the identity function or small deviations from it called residuals. This enables us to build arbitrarily deep networks, where the signal can pass through many transformations or none as needed, allowing the network to learn both deep and shallow abstractions without manually tuning the network depth. Furthermore, it can be shown that adding skip connections dramatically simplifies the shape of the loss function, leading to faster convergence during training. Skip connections were used liberally in the ResNet 50 architecture that won the 2015 ImageNet competition. Although this was not the first architecture to use them, it is the one that made them popular. The ResNet 50 network was far deeper and more accurate than the VGG16 network, but used far fewer parameters. Although skip connections are most often associated with convolutional neural networks like this one, they can also be used to greatly improve the performance of fully connected networks. A logical improvement on the ResNet idea is that of a DENSENET, where skip connections enable a convolutional layer to directly access the information of every layer that precedes it. This is accomplished by using channel concatenation instead of addition to pass the previous information along the network. With this approach, DENSENETs are able to gain higher accuracy in more compact networks with fewer parameters. One may also use small DENSENETs as building blocks in more complex networks. In 2018, the NEURAL-ODE paper won the Best Paper Award at the NeurIPS Information Processing System Conference. It builds upon the ResNet idea by observing that an output of a residual layer is mathematically equivalent to a discrete step in an ordinary differential equation solver, in which case you can replace the discrete solver with its equivalent continuous ODE solver. So this allows us to solve some unique problems, one of which is learning to fit an ODE from data and extrapolating it into the future. So up till now, we've focused on CNNs used for classification. Now let's expand our focus a little bit more to more general design patterns like encoder-decoders. An encoder is a function that maps a high-dimensional input to a lower dimensional representation, often referred to as the latent space. Well, that's just silly. A decoder performs the opposite role. It's a function mapping a low-dimensional input to a high-dimensional output. Encoders and decoders are common design patterns for many tasks in deep learning.
David, do you have a way to turn off your audio or put on headphones?
Yeah, don't worry about it. I don't think that'll happen again.
Okay.
That was just a recording on that slide. The
Okay.
classifiers we've been looking at so far may all be viewed as encoders that map high-dimensional images onto a low-dimensional one-hot vector encoding. In this case, the encoded vector tells us how closely the input data matches each of the target classes. A common and useful type of encoder-decoder is one that takes images as both inputs and outputs. The important information in the image is compressed and encoded in its latent vector, and a decoder takes that latent vector to construct a related image on the output end. If the input and output images are the same, then it's called an autoencoder. But the input and output images can be very different, so long as they have something in common. This setup can be used for image segmentation, single image depth prediction, data fusion from multiple sources, and many more applications. Encoder-decoders are not limited to two-dimensional images. They can have inputs at each end that are 1, 2, 3, 4 dimensionals or more dimensions. 3D volumetric versions can be used for applications like medical segmentation of MRI images, or for acceleration of cosmological structure formation simulations as shown here. An autoencoder is one in which the inputs and outputs are identical. By using a small bottleneck in the middle, the network is forced to learn a compressed representation of the data. The latent vector can be used to store the compressed image and reconstruct it later. This technique is similar to principal component analysis, but with nonlinear component vectors that are customized to your data set. Autoencoders are useful for anomaly detection, as they do a good job of reconstructing data from their own training set, but a very poor job on data that is not from their set. By putting a threshold on the maximum acceptable reconstruction error, we can detect if an image is anomalous. A denoising autoencoder is a variant where the output is a clean version of the noisy input. This can be used to quickly remove noise from the images similar to those it has been trained on. The output from our decoder is not unique, and decoded output can appear to be fuzzy. The encoder maps many high-dimensional vectors to a single low-dimensional latent vector. In this image, we can see that every handwritten digit 6 maps onto the same latent vector. Classifying it is the digit 6. If we then attempt to reconstruct that image, the best the network can do is return the average of all these examples. This average of many handwritten digits appears to be a very blurry 6. We can improve upon this result in several ways. We can make the latent space larger, thereby encoding more information about which 6 we actually want. We can use a UNET architecture, which I will discuss shortly, which also provides more information, or we can use a generative model that selects one single realization at random from the distribution of all possible outputs. So a UNET is a model that was designed originally for medical segmentation, but it's very good at image-to-image mapping of all kinds. It improves upon the encoder-decoder design by adding skip connections before and after each pooling layer. This transforms it effectively into a set of nested encoder-decoder networks, each processing images at a different spatial scale. When decoding, it's able to use both the coarse and fine features to determine its output. Due to its simplicity and effectiveness, UNET is the default go-to option for many tasks. DEEPLAB is another deep neural network designed for segmentation, which is competitive with UNET. There are several versions of the model from V1 to V3+. Some of its unique features are spatial pyramid pooling, dilated convolutions, and an inception-like network-in-network design. We don't have time to delve into the details of this network, but I wanted to mention it as it's highly successful for some segmentation tasks. So next we examine the use of masked convolutions, also known as partial convolutions. Sometimes we have missing or damaged data in our input. When performing convolutions, it would be better to ignore the missing values and only use the valid data. We can accomplish this using partial convolutions, in which we input both our image and a mask describing which pixels are valid. When performing a convolution operation, the missing pixels are zeroed out, and then the sum is rescaled by the number of valid pixels. Typically, the mask is updated and passed along as well. In this video, a user is intentionally damaging the image in order to remove unwanted objects from the scene. The inpainting tries to repair the image by replacing the damaged data with the pixels which are most likely to be there, conditioned upon the valid data. In 2018, NVIDIA published a method based on partial convolutions, which greatly outperform his predecessors at this task, which is what this video is from. There are a lot of useful things you can do with masked convolutions. An interesting example is GO17, which streams damaged data at certain times of year due to a blocked coolant pipe. Masking out the damaged pixels, we can use information from the other channels and features learned from previous observations to repair the damage. Other potential applications are cloud removal from satellite images and filling in missing observations from a sparse sensor array. Transfer learning is a frequently used technique where you use large quantities of simulated data or data from a different data set to pre-train your network, which is then fine-tuned on a small quantity of observational data that you have. Transfer learning works well for inpainting too. In the case shown here, we trained an inpainting network on CMIP5 and 20th century climate reanalysis data, and then used it to fill in missing observations in the HADCRUT4 dataset. The results were accurate and allowed us to improve the estimation of the global temperature trend over time. Please see our paper in Nature Geoscience for more details. Some of the most impressive accomplishments of neural networks have been produced by generative models, which we visit next. Generative models can generate new examples from a given class of data. For example, the face shown in this image is not a real person. Rather, it has been generated using a generative adversarial network trained by a team at NVIDIA. In order to accomplish this, a generative model has to model the distribution of the data. Then a random example is selected from that distribution. See the website, This Person Does Not Exist, for more amazing examples like this. A generative model is useful when you need to generate a single specific realistic example of something. You can use it to generate images, speech, songs, news articles, deep fake videos, or ensemble members for weather and climate simulations. We've already discussed autoencoders. A variational autoencoder is a generative version. Instead of learning a single latent space vector, a VAE learns two vectors, representing the mean and the standard deviation of a Gaussian distribution over each of these latent variables. So first, the input is encoded as this distribution over the latent space. Then a point from that latent space is randomly sampled and decoded to produce a specific example. Once the model has been trained, we can send in our own sample vectors to generate new realistic examples. To date, the most impressive and realistic synthetic images have been produced by GANs. This was an idea invented by Ian Goodfellow and his colleagues in 2014. At its core, a GAN is just a decoder that takes in some random numbers and outputs a realistic sample. In order to accomplish this, the decoder must learn to accurately represent all the statistical details of the target distribution. The innovative trick is to send both real and generated images to a second network trained to tell the two apart. This classifier acts as a detailed loss function that tells the decoder exactly where it went wrong, so it can make a more realistic image. This process is repeated many times until there are no details remaining that distinguish the real images from the generated ones. The discriminator is usually then discarded, and the generator may be used to produce many highly realistic samples. A conditional GAN is one that takes additional input, which it uses to make its generated data more specific. In general, it uses both an encoder and a decoder to form its generator. In this case, the output is built from random numbers and a latent vector that specifies the important features of the input image. Here we see a recent example from Deep Face Drawing paper, where rough sketches of faces are used to produce matching photos. The conditional GAN is trained in a similar manner to the general GAN. However, I find it very helpful to pre-train the generator using a simple loss function before training using the GAN loss. This process I call regress then GAN, and it often helps lead to successful convergence. So here's an example of a conditional GAN I trained to generate realistic GFS total column water vapor fields based on an input image from the GOES-15 satellite. By comparing the generated and target figures, we can see that the input is able to constrain the large scale features, but it's not informative enough to specify the fine details. However, the output looks realistic, and I think you'd be pretty hard pressed to tell which of was the generated field and which one was the actual one. Attention mechanisms and the transformer network are currently having a very large impact on the field of deep learning. The attention mechanism is largely driven by the need for better recursive neural networks. The attention mechanism and its applications has been evolving rapidly since 2014, becoming the dominant pattern in modern language models. More slowly, it's also taking over other non-language-based problems. Before discussing attention, we need to introduce recurrent neural nets, which were talked about in the last talk. A recurrent neural net is a function that feeds information back to itself to be used again the next time it's called. This type of network is able to handle variable length sequences as opposed to the fixed size inputs handled by the networks we've discussed so far. They're useful for tasks like language translation, speech recognition, code completion, or music generation. When the sequence of function calls is unrolled, we see that an RNN behaves like a deep neural network with a variable number of layers. An RNN is trained using backpropagation through time. And just like with deep neural networks, it's very hard to train long sequences due to the vanishing gradient problem. This problem is partially overcome by replacing simple recurrent elements with specialized versions like the LSTM long short-term memory unit or gated recurrent units. Ignoring the details of how they work, they effectively provide a bypass mechanism for training large networks, similar to the RESNET skip connections we talked about earlier. This enables training of RNNs on sequences with hundreds of units, but the problem still persists for longer sequences. So recurrent nets can be used to translate from one sequence to another using an encoder-decoder pattern. A traditional example is translating from one language to another, like English to German. The information in an English sentence is encoded in the latent vector, which is built up over time. The latent vector is then decoded as a German sentence. As each word in the sentence is encoded, the latent vector tries to accumulate everything it needs to know about the sentence. However, if the sequence is very long, the early information can get lost, even when using LSTMs and GRU units. Another big problem is that these operations cannot be performed in parallel, so they're relatively slow. When translating between two sentences, such as German to English, corresponding words can appear in very different places within the sentence. To translate the word slowed in this picture, the model needs to pay attention to the very last word, verlangsamt, in the German sentence. We can represent this by a vector of values, quantifying how much attention we are paying to each of the inputs. As we translate, we have to pay attention to different words, so the importance vector changes from moment to moment. Using the attention concept, we can improve upon the encoder-decoder. Instead of trying to jam all the information into a single fixed size context vector, we can use an attention vector to identify which words are important. The attention vector is generated by an additional shallow fully connected network that takes the decoder state as input. In this way, early sequence information is not lost and much more information can be transmitted between sequences, allowing you to translate very, very long sequences. The transformer is a deep learning architecture based on the hugely influential paper, Attention is All You Need. While attention mechanisms have been used in sequence-to-sequence models before, they were used in combination with recurrent neural networks or convolutions. As the title of this paper suggests, the authors showed that you could dispense with the recurrent neural networks entirely, and that the attention mechanism was all you needed to perform accurate translation. Not only was the translation quality improved, but the entire calculation can now be done in parallel, making it more GPU friendly and lightning fast. A series of language models has been built upon the basic transformer architecture. And for the most part, each has been larger than the last, the most notable of which are OpenAI's GPT models and the BERT model. The latest and largest model, as far as I know, is the GPT-3 model, which has 175 billion parameters. These language models are very powerful and can perform a wide variety of language-related tasks. While transformer architecture seems to have supplanted most other techniques in the area of natural language processing, it hasn't been clear how to apply it to other more general problems. That, however, seems to be changing recently with a rash of transformer papers showing up on arXiv with computer vision applications. Most notably, a paper came out from Facebook AI Research showing how transformers could be applied to dramatically simplify the process of object detection in images. I expect in the near future, transformers will continue to expand their influence. The final topic in this lecture is AutoML. AutoML stands for Automated Machine Learning. And the goal is to automate every task currently performed by a data scientist. If the AutoML idea becomes successful, then everything we've been discussing so far will be totally unnecessary. A few of the tasks we might like to automate include data cleaning, handling missing values, selecting a model, optimizer, and loss function, estimating and tuning your hyperparameters, splitting your data, evaluating its performance, optimizing the trained model, and deploying it. If successful, all we would need to do is provide a set of labeled examples describing what we want our software to do, and AutoML would do all the hard work. While this might be the future of AI software development, for now, we usually need to actually know what we're doing. A sub-goal of AutoML is neural architecture search. The idea is that if we can use an optimizer to search for the best set of weights for a given model, why can't we automatically search the base of all possible networks as well? If successful, we have the potential to widely expand the accessibility of machine learning, as it will no longer require expert level knowledge to build the best network. Also, we can potentially generate unique architectures that people would not have come up with. Shown here is a timeline of some of the major publications in this area, starting with Google's effort in 2016. The original neural architecture search paper used an RNN controller used to design and train a model for 50 epochs. Then it used reinforcement learning to tune that controller to get the best model. Although they were able to find new architectures this way, the computational expense was enormous at around 32,000 GPU hours on 800 GPUs. In 2018, the efficient neural architecture search paper achieved similar results to the best strategies at the time, but it was 1,000 times less compute intensive. It achieved this by using a type of weight sharing for its child models rather than starting from scratch for each of them from random weights. In 2019, the authors of the DARTS paper, Differential Architectures, constructed a method that allows the model search space to be continuous. This enables the network to be optimized using gradient descent instead and backpropagation, and it no longer requires an RNN controller or reinforcement learning to train it. While the accuracy and computational cost are similar to the previous method, being able to use backprop is a huge simplification which makes neural net architecture search far more practical. Okay, despite the length of this talk, we didn't even have time to visit all of the models in the model zoo. But hopefully we got a sense of how many of them are related to each other. Some of the higher level ideas that I would like you to take away are, if AutoML becomes a reality, the average user won't need to know any of this stuff. For now though, there are many different models, each of which is customized for a specific task. The general idea is to encode what you know for certain about your problem and let your model learn the rest. You use pre-trained models and transfer learning when you can to save on training costs. And keep in mind, the state-of-the-art models of today will be completely discarded tomorrow. Use the Archive Sanity website to keep up. Thank you for listening, and if you have questions or would like to collaborate, please feel free to contact me at dhall@nvidia.com.
All right, thank you, David. We'll go ahead and take questions for about we have about 20 minutes worth of time for questions, or 10 minutes. Sorry, we'll be wrapping up at 12:20.
All right. First question: how do I make the choice of using a common CNN architecture or building my own model for image classification? So if you can use a common architecture that is pre-trained, you should definitely do so. It takes a lot of compute time and power to train your model, and it's very wasteful to start over from scratch if you don't need to. So if you're doing object detection of standard objects, cats, dogs, planes, whatever, just use a pre-trained model. Download one of the great ones off the internet. If you're using something close to that, you can start from that model because the weights are already almost where you want them to be. But then you do a little fine tuning. You train for a few epochs on your data. That's the transfer learning idea. Still, you didn't have to do much training, saves you a lot of compute and time, but you get your objects to be identified. If your objects do not fit any of the previous models, you have special data formatting, whatever, you'll have to build your own. If you want ML to find atmospheric rivers, how would you go about doing that without defining the features of atmospheric rivers for it? So Karthik and his group actually did this. They created a website where you're able to actually have experts outline where they see atmospheric rivers. So every time there's an atmospheric river on the screen, they draw a little outline and it tells the neural network that there's an atmospheric river there. So you basically have labeled a positive example. So you show it images with positive examples, images with negative examples, And then you train your neural network on lots and lots of those. And it finds its own features. You don't have to tell it anything else. So if you have enough data, you can amazingly solve these kinds of crazy problems where you map an image to a number. So the image is the input satellite, and the output is 1 or 0. Yes, I have an atmospheric river, or I don't. It finds that function all by itself. Do you know of any work to guarantee that the output from GANs obey physical constraints? After all, output may qualitatively look correct and fail physical laws. So this is a very good question, and it is the topic of physically guided neural networks, which is a big field all of its own. There's lots of ways to try and make sure your neural networks obey physical constraints. You can apply a loss function to deviations from them. So for example, if your output is supposed to be conserving energy, you can apply a penalization term to that to make sure it gets closer to obeying the conservation of energy. You can also hard code these things into your network. If it outputs certain terms or pixel values, you can make sure that some of them are the average of the others. So like your last equation can be exactly satisfied. And then you can also use projection methods where it maybe produces something close to energy conserving and then projects onto that space. All of these things can be coded up within your neural network, either implicitly or explicitly. There's a lot of ways to do it. I can go on for a while, but I think I better move on. Is there a way to calculate both spatial features in CNN and temporal features from LSTM? Can we combine or use both spatial and temporal features for predictions? So yes, I haven't done a lot of this, but there are definitely neural networks that combine these two. There's actually quite a few of them. One of the simplest is basically a modified UNET network where they have little sequence detectors inside each of the convolutions. So yeah, there's a bunch of custom networks. If you contact me, I can send you some references, I guess, for those. But yeah, convolutions in time separated from convolutions in space are possible. You can also do space-time convolutions using 3D convnets or 4D convnets. Can you please tell me about creating ensembles by generative models using examples for earth science? So I guess you might be talking about ensembles of weather predictions or climate model predictions. So yeah, so I guess you could think of a generative model where you have output from a weather prediction model. So it has a specific prediction of what the weather will be in a day or two. And you generate many of these, and because of the random initialization, you get a bunch of different ensemble members. So that's sort of your GAN right there. You have a data set that it can learn. And then you can train your GAN to generate new unique values from that data set. So if you train this on lots of different examples on different days, you can eventually just input a few or very few examples of what you want it to produce, and it can produce a large number of ensemble members, which you can then average over and produce a more accurate prediction. I haven't actually done this, so I'm being a little bit hand-wavy here, but I think a conditional GAN could actually help you generate better ensembles. I haven't read a paper explicitly on that, although I'm pretty sure somebody's done that by now. What happens in each layer? How do you try to reduce the gradient to get closer to your target value? So what happens in each layer is basically that backpropagation problem that Karthik explained in pretty good detail. But the idea is you have an error function, a loss function. It tells you how good your model, which is just a big old mathematical function, predicted the right answer. And you measure it and, oh, it was wrong by such and such a value. Then you split up the error and send it back to the neurons in the previous level. This is done using the chain rule, just how much of the error goes to each of those neurons. And you adjust the weights to those neurons. And then you split the error from each of those activation functions up in exactly the same way. You just iterate on that as if they were the loss function, and you send their errors back and back and back. So each weight gets adjusted up or down a little bit if it was too high or too low. And what it does overall is it just basically descends that loss surface to a very low error value. In the end, if it converges, you have a function with very little error, which means it does what you want it to. So if you get a function that converges on your data, well, you've magically written a piece of software that does whatever the heck you wanted it to do. Are we going to run out of energy to run these deep learning models as the amount of data is exploding? What is your take on quantum computation? Huh. Interesting questions. Yeah, so a lot of people complain that deep learning is very power hungry. And of course it is if you're training 32,000 GPU hours on 800 GPUs. That's basically insane. But deep learning models are just another type of computer program. So when you're training them, it does take a lot of energy, but so does running a climate model. You know, they're both expensive calculations. Once you've trained a deep neural network, actually it can be much, much faster than the software that it might be replacing, in which case you're actually saving huge amounts of energy. But yeah, data keeps growing, the models keep getting bigger. So yeah, I mean, you know, there's an energy problem there. We want more and more efficient network design over all the time. What is my take on quantum computation? Once quantum computing works reliably without having so much noise that you have to sample the same thing 10 or 20 million times, it's going to, of course, overtake normal computation because it can basically come up with impossible to solve problems instantly. But that's still a long way off, I think. We'll have to see. Will the CNN learn about rotated images as well as shifted images at the same time? No. So all we've encoded is translational invariance. We move our matrix around and say the cat could be here or here or here or here. But if the cat is tilted, it looks like a different object. So people handle this by doing data augmentation, which is basically giving it tilted versions of the cat and different angles and flipped. And then it learns all these different features for the cat. You could also encode explicitly rotations in there, just like they did with translation. So I've never seen a rotation translation invariant CNN, but I think you could probably do it. That might be an interesting paper for someone. So any invariants that you can come up with, you could encode explicitly and save yourself all those data augmentations. How do you find out that the model is identifying low-level and high-level features at some hidden layer? That is a very good question. So there's a lot of ways of attempting to visualize what's going on in each of these models. So you can take a single activation or neuron, or even a single layer, or even a single output, and adjust the input up and down until it massively basically activates that one single function. So this is a way of seeing what in the input that neuron is responding to. There are also lots of other ways of visualizing what neural networks are doing. Karthik showed a few in his slides. I believe Amy McGovern will possibly cover this in her interpretable deep learning talks. So yeah, there's lots of ways to see what they're doing. None of them is perfect. And the images in that figure talking about that, there's a reference at the bottom so you can see how they did it. Can you describe how we can set up rainfall prediction problem with machine learning framework, assuming that we have radar satellite images? Rainfall prediction. So, all right, so you have radar images as your input. And what you have is presumably measurements of precipitation on the ground at stream gauges. And so all you're basically doing there is attempting to produce a function from the radar images over a series, probably a time sequence of radar images, to the streamflow function as the output. I did something simpler, but similar to this before in time. So basically you're just finding a function from the sequence of radar to the streamflow and precipitation values. So yeah, if you have enough observational labeled data from your radar and your gauges, you should be able to, you know, your weather model predicts what the radar frame will look like in the future, and then you can predict how much rainfall it produced. Or, you know, you can do the thing where you attempt to directly predict the forecast using deep learning model as well. So there's like, you could have layers and layers of these functions working together. Let's see, do I have time? I think a little bit. What's the best way to combine various sources of observations? In situ, remote sensing, model simulations to train a model and produce geophysical parameters. I'm not exactly sure what the question's asking to produce, but basically you use simulations to augment the data whenever you don't have enough of the real data that you want, because it can be very expensive to label the data by hand. If you're, yeah, I'm not sure exactly what you're shooting for with this question, so I'm not sure what's the best answer here. If you're talking about physical parameterizations or something else, maybe if you clarify the question, I can help answer it better. So I'll skip to the next one. What values are used in the kernels used with the different CNN architectures? Are these hyperparameters which can be set? So the kernels are learned. So before we had learned the all the connections in a fully connected layer. The convolutional neural network is doing exactly the same thing, but it's just not connected to everything. It's connected to small groups at a time. Those weights are learned, and they are not really hyperparameter. You can generate, the hyperparameters are how large your convolutions are and how many kernels you want to learn, and their stride and things like that. But you don't specify the values within the kernels. You let them learn those from data. I see David Gagne, so I assume I'm out of time.
Yep, let's thank David Hall one more time. And thank you for listening to all these great presentations this morning on deep learning.
Thanks,
if you have more questions, we're going to have a panel session with the speakers from today from 1:20 to 1:50 p.m. Mountain Time. Then we'll have a quick hackathon update, and then we'll conclude the lecture portion at 2 o'clock. So we'll see you back at 1:20. Thank you.